In this question, I'm asking you to provide a mechanism for how this starting cyclic ether, when treated with aqueous sulfuric acid, turns into this specific molecule right here, which has an alkene functional group and the alcohol functional group. So remember, anytime you're given a mechanism question, don't worry about major product, don't worry about minor product. Don't say to yourself, well, wouldn't this instead form this product? That is not the question you're being asked. You are just being asked, how did this structure form when these reagents are treated with each other? Give a logical mechanism. Okay. All right, so let's just go ahead and start with this one. I'm going to draw this out. Sorry, it's not as neat. I'm not taking my time on this one. All right, so we just have to think about what's going on here. So we have sulfuric acid. We can write that as H3O plus, the hydronium ion if you want. Not a big deal. I'll just draw it out here. So here's sulfuric acid. It's a non-nucleophilic acid. Well, remember, every time you do mechanisms, the flow of electrons is what you're showing. So always write these negative to positive. The arrow should go away from the electrons and towards something that has a full positive charge or a partial positive charge. All right, so here I'm showing the electrons of the oxygen grabbing this proton. It has a partial positive charge. The electrons between the hydrogen and oxygen remain on this oxygen here. Right? So that's going to give us this structure here, the proton on the oxygen, and we have a positive charge on oxygen. All right. Now, what can happen next here? Keeping in mind that we want to form this product right here. You can clearly see this was a ring and it opened up. So the next thing that can happen is oxygen can grab the electrons around it. It can grab these bonding electrons or these bonding electrons. But which way is it going to go? Well, if this bond breaks, that forms a primary carbocation. We know those aren't stable enough to form. If this bond breaks, it forms a tertiary carbocation, which is stable enough to form. So these electrons are going to move there, which means that this oxygen is leaving this carbon. So this carbon is going to end up with a positive charge. I'm going to keep this kind of drawn the same just to sort of help visualize this. So what I mean is I'm just going to kind of keep everything kind of where it is, but with the bonds broken. All right. So that's going to put a positive charge on this carbon right here, right? So the ring is open at this point, but we have a double bond here. So we got to think about what could the next step be to form this double bond right here. Well, we have a carbocation right here. That's going to render any of these adjacent protons on this methyl or this methyl or this methylene group, it's going to render them more acidic. And since we're in a non-nucleophilic acid like sulfuric acid, it's going to form the most internal double bond. So what's going to happen here is one of these protons are going to be removed from this carbon right here. Something in here is going to act as a base and remove that. It could be the conjugate base of sulfuric acid. It could be water. It could be the starting ether. Something in here with lone pairs is going to remove that proton. I'm just going to show water doing it. So it's going to grab that proton, form this double bond here, and that's going to give you, I'll keep it kind of drawn the same, going to give you this structure right here, which is the product we're being asked for. So here we provided a logical mechanism for how this cyclic ether reacted with aqueous sulfuric acid to form this molecule right here.